We solved some exponential equations, and continuing section 4.5, we are going to look at some logarithmic equations now. Now, just like with exponential equations, there are two main types that you want to consider, and your approach would be different depending on which type of logarithmic equation you have. An equation is considered a logarithmic equation if you have a variable inside the logarithm, like these two equations. These are two different equations, and again, just like with exponential equations, you want to see if you can have matching bases where you just drop the logarithm, or do you have to use exponents to rewrite your logarithmic equation. In this first equation, we see that we have exactly the same logarithm on both sides. Log base 3 of something equals log base 3 of something. The only way that can happen is if those two somethings are exactly the same. And you can check this in your original equation. If you plug in 2 for x, yep, you get a true statement. So it's that easy. If you can have exactly matching logarithms with the same base on both sides of the equation and nothing else. One log on one side, one log on the other side. In this next equation, we have log base 3 of x on the left again, but we don't have a log on the right. We have a number on the right. When that happens, we use that property of logarithms that relates them to exponential equations, and we rewrite this in exponential form. We say 3 to that power equals that x. And now it's not a logarithmic equation anymore. In fact, we're done because we know 3 squared is 9, and that gives us our solution. You can check it. If I check it on the side here, log base 3 of plug in 9 for x, is that equal to 2? Yes, it is. So that solved the equation there. So you want to look for these two forms. If your equation doesn't look like one of these two forms, then see what you can do to make it look like that. You may have to use properties of logarithms like the product law, the quotient law, the power law. You might have to do some algebra, subtract something from both sides, divide by both sides by something to make it look like this. So in both of these forms, you just have one log on one side, and then in one form, you also have the same type of log with the same base on the other side, or you just have, this is normally a number on the other side of the equation. If you have that first form, it's just like matching bases with exponential equations. You are just going to drop that logarithm. So if log base b of x equals log base b of y, then just you have x equals y. If you have the second type, let me get rid of this, where you don't have log on both sides, you have just the log on one side, and then this is usually a number on the other side. Then you want to convert it to exponential form. Remember, we said b to the power y equals x. And now it's not going to be a logarithmic equation anymore. B to the y is something somehow related to numbers, and you can just solve for x. Always give exact answer and approximations as instructed. This step 4 is not optional. This is mandatory. You have to check your solutions in your original equation. And really your concern is you don't want to end up with anything negative inside a logarithm. Because remember, domain of logarithmic functions is positive numbers only. Let's look at some examples. We have a couple of equations here. In the first equation, I have a log all by itself on one side. And then on the other side, I don't have a log. I have a number. So that is like the second form, log base b of x equals y. When that happens, as long as your log is on one side by itself, then we just use that equivalent form, that's the exponential form. We say that base to that power equals the argument. So we rewrite this. 3 to the third power equals 2 minus x. And this is in fact just a linear equation. You just have to clean it. There's nothing to kill. 3 cubed becomes 27. And you can subtract 2 from both sides. And then divide both sides by a negative or multiply by a negative. But before we box this up and accept it as a solution, we have to plug in negative 25 in our original equation. And you can check this all the way, see if it gives you 3, but really all we're interested in is this number that we get inside a logarithm. We just don't want it to be negative. And this one isn't. 2 minus negative 25 becomes positive 27. So yes, indeed, it does check out. The solution to this equation is x equals negative 25. In the next equation, I have logs all over the place. I have 2 logs on the left and a log on the right. So it's not going to be the type where we will get a number on one side. We can make it look like this, where we have a log on one side and a log on the other side, except that we have 2 logs on the left-hand side here. Well, we can use our property, that law that says log of something plus log of something else can be written as long as the bases are the same, log of the product, x times x plus 1. And now I can see that I have log base 5 of something here and log base 5 of something here. So that means I can just drop the logs. And in order for the logs to be equal, the arguments must be equal. So we have to solve this equation. Every step of a problem is a new problem. It's a quadratic equation. Let's distribute the x. Put everything on one side. And this one can be factored pretty easily. Plus 5 minus 4. Set each factor equal to 0. We get our 2 potential solutions. We have to check them. Remember, in the original equation. So original equation, if I plug in negative 5 for x, I'm already in trouble with that very first term. Log base 5 of negative 5, that's not going to be defined. I cannot accept that. So then I'll try 4. If I plug in 4 here, that's good, that's fine. If I plug in 4 here, that's fine. So that is our only solution for this equation. Here are 2 more examples of logarithmic equations. An equation, again, is logarithmic if there's a variable inside a logarithm, which we do have here. And I have a couple of ln's on the left and some ln's on the right, so I am going to use that property that says if I have log base b of x equals log base b of y, I can just drop the logs and I get x equals y. Well, the problem is I don't have just one log. I have to condense these 2 into 1. So that would give me, because it's plus, I multiply x plus 2 times 3. That's the product law of logarithms. Same thing on the right-hand side. It's plus, so I get 5 times 2x minus 3. Now the ln's, I can just drop. If ln of something, this is log base b, and that works for any base, and ln is just a logarithm base e. So the same thing applies to that. So I get x plus 2 times 3, which is 3x plus 6, equals 5 times 2x minus 3, which is 10x minus 15. I will subtract 3x from both sides, and then add 15 to both sides, then divide by 7, and we get x equals 3. Before I box it up, I better go check it in the original equation. 3 plus 2, 5, that's okay. That's allowed. 3 Here, 2 times 3 is 6 minus 3 is 3. That's positive. That's allowed. So I will accept that solution. In the next example, I have a number on one side and a couple of logs on the other side. I have to condense them into one log. There is that minus in between these two logs. So that means I can use the quotient law or quotient property of logarithms, which says if you have log in any base of something minus log the same base of something, then you write the quotient of those arguments. So now I have this form of the logarithmic equation, and remember that for those, we rewrite them as exponential. The base for this equation is, for this logarithm is 3, so I get 3 to the second power equals that whole argument there. So I write 3 squared equals x plus 15 over x minus 1. Well, this is a rational equation. I have to get rid of that denominator. 3 squared becomes 9. Let's do that first. And then we will multiply both sides of the equation by the denominator, which is x minus 1. That gives me 9 times x minus 1 on the left, x plus 15 on the right. And we just distribute the 9. This is just a simple linear equation now. Subtract x from both sides, and at the same time, I am going to add 9 to both sides. Wow, 3 is a popular answer for these equations. Oops, I boxed it up too soon. I really should go back and check over here. If I put 3 here, 3 plus 15 is 18. That's positive. That's okay. 3 minus 1 is 2. That's positive. That's okay also. Look for more examples in your book for examples of what happens. Again, a couple more maybe when the number cannot be accepted because it gives you a negative inside your logarithm. One last thing I wanted to talk about to wrap up this section is to how we can solve any equation using your calculator. Now, this equation here is exponential, but then it's also got these polynomial on the right-hand side. So we actually can't solve this equation algebraically, but we can solve it graphically. The way you solve any equation graphically, one way, is to just enter the left-hand side of your equation into y1 in your graphing calculator and the right-hand side into y2, and then find the point of intersection. So we just go to y equals and put e to the, so here's the e to the x squared, so I'll do x and then squared. To get out of the exponent, I'll use the right arrow and then minus 2. That's the left-hand side of the equation. And then I go down, and in y2, I will put the right-hand side of the equation, x to the third power. With the right arrow, I get out of that exponent, minus x. So we can just look at the standard window first to see what this looks like. So that's the graph of y1, which is e to the x squared minus 2. And that's the graph of y2, which is x cubed minus x. So where do these become equal is where they intersect. We've done this before graphically, but not on the graphing calculator, I don't think. So it's kind of hard to see, so maybe I'll zoom in right on the origin. So it says x equals 0, y equals 0. I have to press enter for it to zoom in there. And we can see there's a point of intersection right there, and there's a point of intersection there, which is where the two y values become equal, which is going to be the x that gives us a solution. So there's two of them. How do we get the calculator to find these two? You go to Second, Calc, and as you might guess, it's that option 5 for intersect. Then it's going to ask you some questions. Y1, first curve, yep, that's the one, so we press enter. Y2, second curve, yep, that's the one. And then for the guess, I would just get close depending on which solution you're trying to find. I want to find that one on the left first over there, so I'll just get close. You don't have to get that close, but you just kind of get close and press enter. And it gives you the intersection. So that's one of the solutions to this equation. You can round to however many decimal places. You do not need to worry about the y because there is no y in this equation, only the x. So that's one of the solutions. To find the other one, you repeat the process, intersect, and then first curve, yep, that one, second curve, yep, that one. And then with the arrow, we are going to get close. Now, it just says guess. Yep, that's a good guess right there. And it gives you the other solution. It's about 0.7 something. So you can solve equations using your graphing calculator by putting the left-hand side into one y and the right-hand side into another y. Of course, you have to make sure that you have a good window to see everything that's happening in the graph, and then use the calc menu and intersect to find the solutions.